My project was the development of photocatalytic technologies for aquaculture water treatment. Clean water is very important for public health, and as there's technologies out there that help us to create this clean water, removing pesticides and pollutants, and these technologies include filtration and absorption and thermodistillation. But one disadvantage of these technologies is that they don't fully eliminate the pollutant, so they can just concentrate it, so they fail to eliminate it efficiently. But for my project, I concentrated on a technology called photocatalysis. And what photocatalysis is, if you break it down into two words, the photo part meaning a light reaction and the catalysis coming from the use of a catalyst. By using a catalyst such as titanium dioxide or zinc oxide, then we can combine that with an irradiated reaction using a light, and this enables the breakdown of a pollutant such as a pesticide or a herbicide, and it eliminates it by breaking it down at a molecular level. And the advantage of this is that there's no residue that needs disposed of afterwards, so it's a very green and environmentally friendly way of dealing with pollutants in our water systems. So MCPA is a pesticide that is used by farmers, and especially in this area of Ireland, and MCPA is used by farmers to treat broadleaf weeds and rushes. So what can happen is, if used incorrectly, the pesticide can leach into waterways through runoff or through improper spraying methods. So by the MCPA getting into the waterways, then it can cause a problem for public health. So it's important that we come up with some way of being able to eliminate this from our water systems. In comparison to other pesticides that's used in agriculture, MCPA is a very toxic pesticide. And the problem is that in Northern Ireland there is many sites where MCPA exceed the European drinking water limits by sometimes up to 8 times. So it's, especially in Northern Ireland, it is a fairly major issue. So I'm a Bryden Centre student here at ATU Donegal. I have a supervisor based here in ATU Donegal, and I have 2 supervisors based in Queen's University in Belfast.
What our area of expertise was really in electrochemical sensors. This is what Wesley had done previously, was in the area of electrochemical sensors, what he'd done his masters in. So if you like, we've married those two together in the Bryden project, where the expertise in photocatalysis came from Queen's University Belfast, while the expertise, a little bit of expertise in electrochemistry or electrochemical sensors was already established with Wesley during his master's project, and that allowed us to then, if you like, provide a different means of monitoring the photocatalytic reaction. Nobody had really monitored photocatalytic reactions using electrochemistry or electrochemical sensors before. So, of course, what Wesley does here in the lab is only on a small scale. But I think from the reactor that Wesley has built there, I think probably people can see the potential for building that into something bigger.
Part of my research here in the ATU in Donegal was to do some lab work, try to apply photocatalysis to break down this MCPA pesticide. The initial stages of it was to build a photocatalytic reactor. I came up with the idea of having it in a stirred solution, and I came up with this idea of having an overhead stirred solution in this beaker that's capable of holding 3 litres. It's driven by an overhead stirrer. We can set this at different RPMs, and so we found the optimum stirring speed. You can see around the outside of the beaker here we have LED lights, and we just connect them up like that. Inside the beaker you'll see the rotating paddles, and we've got these 3D printed up in the engineering department here in the ATU. The shape of them, we came up with this shape here so that we could fix the netting substrate, or the netting pieces. This is what we came up with. These are small nylon netting pieces, and onto this nylon netting pieces we immobilised the titanium dioxide, or the photocatalyst. And to look at it with the naked eye, you don't see it, but it is there. So here's the photocatalyst as it is, it's just a white powder. So we came up with like a sol gel, so we got that applied to the netting substrate. So at different time intervals, we take a sample. My detection method for analysing this was an electrochemical technique, so to do with voltammetry. So we just transfer it then to our small cell, and then once we press analyze or press play on our system, we get this style here of a red line, and we can see a peak here. So the peak here is a representation of MCPA in our sample. Where the peak is along the x-axis is qualitative information, so it tells us that it is MCPA. Where it is along the x-axis, where it is along the y-axis tells us how much, tells us quantitative information. To carry on this work, we'd like to maybe scale it up again, design another type of reactor maybe with these types of reactors in series, or maybe increase the volume of the reactor that we've built. So this could be of benefit to water treatment plants whose primary job would be to try to create these clean waters free from pesticides. First of all, it was really difficult to get the catalyst to anneal to the netting, so that was a procedure on its own to get that to work. Most studies using photocatalysis just take this catalyst and add it into what they call a slurry solution. The problem with this is that it's mixed all through the actual water, and it's the removal after the treatment process has taken place. It's the actual removal of the catalyst from the water that's the problem. But by immobilizing it onto the netting substrate, then there's no removal of the catalyst that's required after the reaction is finished. The concept that I've come up with regarding the reactor could be brought forward, as I said, that maybe scaled up or working on a different style of reactor, but the principle is there, that this reactor design has worked and is capable of degrading this pesticide in such a small length of time. So it might be of interest to those in the treatment plants, or it could be of interest also to farmers who are using the pesticide daily. So if they have any amount of it that they need getting rid of, they could use this technology as well. So I'm finishing up my PhD hopefully in June. After that I would like to continue on in research, ideally as a postdoctoral researcher, and there'll be an opportunity arise here in the ATU Donegal for me to continue on the work. I'd like to work with the Environmental Protection Agency, as this pesticide is a major concern for them. They have quite a bit of research put into this pesticide, the problems that it's creating. To work along with them would be ideal for me going forward. So I've really enjoyed my time, first of all, working with the Bryden Centre. It's been a real good experience, and I'm very thankful for the funding that I've received, the connections that I've made through the different universities, and especially the summer schools that we've attended to. It's really opened up connections with other people, with other researchers, even inside the same topic, and it's good to talk to other people on the same line of research. So it's been very enjoyable, and I've really enjoyed my time with the Bryden Centre.